And the next speaker is Professor Shaoqin Ruan. Professor Ruan is Assistant Professor in the College of Civil Engineering and Architecture, Zhejiang University. His research focuses on life cycle assessment and costing of cement and concrete production, carbonation of MgO and cement and their applications in civil engineering, reviews and recycle of industrial and construction waste as construction materials, straining, hardening, and self-healing behaviors of cementitious composites, 3D printing concrete technology. Today, his topic is life cycle assessment of alternative materials used for stabilization and solidification in some cases study. Now, let's welcome Professor Ruan.
Good afternoon, everyone. So I'm very happy to join this web seminar. And today, my topic is life cycle assessment of different alternative materials used for stabilization and solidification. And now I'm working in Zhejiang University. So my presentation can be divided into 4 parts. The first part is about introduction, then is the methods that we use. The third part is about the results and discussion, and finally is the conclusion. So first about the introduction, as we all know, the SS or stabilization and solidification is a process that results in the immobility of contaminants in hazardous wastes through reactions with additives or processes. And we all know Portland cement, it is very cost effective and it is widely used in SS. But its production process is quite energy intensive and emits a high amount of carbon dioxide. Nowadays we try to achieve the goal of carbon neutrality. So if we use too much Portland cement in SS, it is not quite environmental friendly. So we should search for other materials that is low carbon. And I will show you 2 figures first. First is about the materials flow of ordinary Portland cement manufacturing. And we all know, first you need to get some raw materials to produce cement. And I know it is quite boring, but I want to introduce this first. And you need the lime, alumina, silica, and oxide. Then you need crushing, grinding, and blending to make this is blended mixture. Then the very important procedure, that is calcination, and you can get some clinkers. Then finally you add some gypsums to Portland cement to produce the commercial products. And we all know the carbon dioxide emission that it can be divided into 2 parts. The first part is about the direct carbon dioxide emission. The second part is the indirect carbon dioxide emission. And the direct carbon dioxide emission comes from the calcination of carbonates, the calcium carbonates. And the indirect carbon dioxide emission comes from the use of fuels. If you use some coal, if we use some natural gas, it will produce some carbon dioxide. And in terms of OPC, around 0.8 ton carbon dioxide will be emitted to produce 1 ton OPC. But actually, it depends. It really depends. And it depends on the locations, depends on the regions, or depends on the technologies you used. So this value, 0.8, may not be that accurate, and it is highly variable. So in terms of this, we need to search for a low carbon binder for the use of SS. And the second figure is about the process flow, indicating the energy, heat, or gas or solid emissions for the generation, for the production of OPC. And it shows some energy you need input in, and also it will emit some gases or solid wastes during the production of OPC. Here comes the question. So are these binders, that so-called low carbon binders or industrial waste, are they really low carbon? So here we need to use the very powerful technique or the method that we call the life cycle assessment. And the life cycle assessment, it can be divided into 4 parts. And the first is about the selection of the boundaries of scope and system during an LCA. The second part is searching for first-hand or second-hand inventories of a product or process. That is the evaluation of the obtained data using an impact assessment method. Finally is the interpretation of outcomes and providing recommendations for improvement. So there are numerous methods that we can use to evaluate the environmental impacts of some materials or the procedures. And the most the widely used one is the INCO indicator 99 or IPCC 2013. And INCO indicator 99, it can be divided into several parts, and you can get a number of midpoint categories such as the climate change, the radiation, the land use, and these environmental categories can be further categorized into 3 groups, and that is the damage to human health, damage to ecosystem, or damage to resources. And after you get the endpoint results, you can weigh these values, and finally you get the interpretation. And in terms of IPCC 2013, it is usually used to obtain the carbon dioxide emission during the production of certain materials or a certain process. So still, of course, we need to first talk about the ordinary Portland cement. And this figure is about the normalized impact categories with respect to climate change set at 100%. And as we can see from this figure, the fossil fuels are identified as the largest impact category to produce the OPC in the USA and Europe. But due to the confidential issues, China's actual carbon footprint due to the cement production is still not fully unknown. So in terms of this, we have several measures that to increase the sustainability of OPC or Portland cement. The first is about the energy type and efficiency. We need to increase this. And for example, we use lower carbon fuel like natural gas. And the second is we need to increase the efficient grinding and conversion from a wet to a dry process. And the third method that we can use the replacement of the out-of-date kilning lines or introduction of high volume of supplementary cementitious materials. Okay, so previous speakers also mentioned some binders like alkaline-activated cement, and actually this type of cement is quite popular in my research area. And nowadays, numerous researchers, they investigated the performance of alkaline-activated cement, whether they are used in the concrete or used in the SDS. So actually, I want to give a very brief definition of ASC. That is, alkaline-activated cement is considered to be a more sustainable material than OPC, which is produced by a reaction between the aluminosilicate-rich materials and the alkaline activators. And in terms of its advantages, ASC shows greater sustainability than OPC, and ASC demands lower energy and carbon footprints. However, there are some uncertainties. In some cases, ASC may show a higher global warming potential compared with blended cements, which could be related to the production of alkali that consumes a large amount of energy. And as we know from the definition, to produce or to prepare the alkaline-activated cement, you need a large volume of the alkaline. And this alkaline, in terms of this alkaline, its production process may be energy intensive. So it further add some environmental burdens to the whole process. And the second part is about the magnesium-bearing cement. So first, I will briefly introduce about the MgO, because MgO is the major component that is used in the magnesium-bearing cement. And the magnesium oxide produced from the dry root. The dry root is about the calcination of the magnesite. as you can see from this equation, it will produce the magnesium oxide and the carbon dioxide. And the second part is about the wet route. The wet route is about to obtain the MgO from the seawater, brine, or rejected brine. You need some alkaline bases to produce the magnesium hydroxide first. Then you calcinate these products to produce the MgO. But from our experiment, that we find that the MgO produced from the dry route has an advantage over the MgO produced from the wet route in terms of the overall sustainability. And you can see from this figure, the left one, MgO from the dry route, it has a lower single score compared with the MgO from the wet route. And however, in terms of the dry route, magnesite, the major production countries is China compared with in terms of the MgO production. So if you want to use the MgO from other countries than China, the transportation, is needed, and it will also lead to some environmental impacts concerning the transportation of MgO. Then, there are several types of the magnesium-bearing cement. And for example, the carbonated MgO cement, magnesium-silicate-hydrate cement, magnesium phosphate cement, magnesium oxychloride cement, and magnesium oxysulfate cement. And the magnesium phosphate cement, magnesium oxychloride cement, and the magnesium oxysulfate cement, they all show very, reveals rapid setting and hardening properties, and which is quite useful in the process of SS. So they are commonly used in a lot of applications. And first about the carbonated MgO cement, and we published a lot of papers regarding this area. And as we know, the MgO cement will acquire the compressive strength via sequestrating the carbon dioxide. So it will then lead to the reduction in the pore volume and the improvement of the microstructural process. And the MgO, the carbon dioxide, can be permanently captured in the form of stable hydrated magnesium carbonate. However, the carbon dioxide sequestration potential of MgO used in the SS in a natural environment is still unknown, because due to the lack of the geochemical model. And you can see from this figure, the MgO will first react with water to produce some layers of brucite on the surface of the particles. Then it will also further react with carbon dioxide to further produce the HMCs. That is called the hydrated magnesium carbonates. And then it will lead to the production of the pores and lead to the strength improvement. And previous speakers also mentioned about the MICP. I know, yeah, MICP is also a quite popular research direction in this area. And it uses the bacteria, and it uses some calcium-bearing salts, like calcium chloride, calcium, salts. And actually, previously, we also conducted some research regarding the use of MgO in MICP. And we also introduced the reactive magnesium cement and the bacteria, and to produce the hydrated magnesium carbonates to solidify these sands. And the results are quite good, and I think it is a very promising field. Then is the magnesium-silicate-hydrate cement. Actually, magnesium-silicate-hydrate cement can be synthesized by the reaction between MgO and a silica-rich source, such as the microsilica and the rice husk ash in the presence of water. And this salt, the sodium hexyl phosphate, instead of PCE, and is used as a reducer, water reducer. However, this one, when you use this water reducer, it may add additional environmental loads to the MASH binders. And also in terms of the solid waste, normally people researchers use the microsilica, and however, some researchers also use the rice husk ash as the solid waste to produce the MASH cement. And however, this silicon dioxide should be amorphous, and then if it is crystalline, and the MSH, the strength of the MSH is quite low, so it may not be very effective in the SS. That is magnesium oxychloride cement. And MOC, we call this MOC. MOC is a type of the non-hydraulic cement by the reaction between the MgO and magnesium chloride. And several very important phases like phase 3 and phase 5 are the major products that formed at an ambient temperature, which contribute to the fast hardening of cement paste. And there's a study that is over the past 15 years, the rate of carbon dioxide will be further recaptured into the MOC. And it is found that the rate of carbon dioxide capture is about 0.07 kilograms per square meter sample per year, and accounting for 20% to 40% CO2 resequestration owing to the natural carbonation of a 15-year time frame. So this equation is about the carbonation of MOC. So when you perform an environmental assessment of MOC, its capture potential of carbon dioxide should be also taken into account, and to make it a more comprehensive evaluation. That is the magnesium phosphate cement. Actually, this one, we conducted several research about its feasibility in the 3D printing, and found it's quite effective because it is rapid setting. And MPC is also a type of ceramic via the reaction of monopotassium phosphate and MgO. And the produced crystal structure is this one, and struvelite, and contributing to the rapid strength development in binders. And produce 1 ton of MPC and OPC, the energy requirement is quite different, and the energy requirement of MPC is much lower compared with that of OPC, and the carbon dioxide emission of MPC is also only about 0.32 ton to produce 1 ton MPC, so which is almost 3 times less compared with the counterparts of OPC. That is the magnesium oxysulfate cement. And magnesium sulfate cement, it consists of MgO and the magnesium sulfate. And I performed several evaluations regarding the overall sustainability of MOSC and OPC. And we found that is the ratio of MgO to magnesium sulfate is irrelevant to the final environmental impacts, and they're quite similar. And the overall sustainability of MOSC is comparable with that of OPC, so which means it is not quite sustainable. And in terms of the carbon dioxide emission, and an interesting thing is that is the production of MOSC emits much higher carbon dioxide emission compared with OPC, which means if you want to achieve the goal of carbon neutrality, you should not use the MOSC. Instead of, you should use OPC. Maybe it's cheap and it is widely used. So MOSC may be not very favored in terms of the carbon dioxide emission. That is the calcium sulfur aluminate cement. And maybe I mentioned in the previous slide that is in terms of OPC production, you need to calcinate the limestone, that is calcium carbonate, to emit a lot of the carbon dioxide. But in terms of CSA, a source of sulfur is needed in the manufacturing process, and an additional extra source of aluminum oxide is required due to the limited source of bauxite, which adds to the environmental burden due to their mining and refining. So the sustainability of CSA is highly dependent on the local or regional availability of bauxite. But in terms of its advantage, yeah, of course, it has a lot of advantages. For example, its production emits less carbon dioxide emission than OPC, because you don't need to calcinate the limestone, that is calcium carbonate. So the direct carbon dioxide emission is much lower, which led to the lower overall carbon dioxide emission. Meanwhile, the manufacturing process efficiency of CSA is much higher compared with OPC. And while the use of industrial waste, the CO2 cement is more effective in the process of SA sustainably. Then here comes the question, that is it sustainable to use industrial waste in SS? So yeah, I have some comments, critical comments. That is, first, actually some industrial waste may be quite radioactive. Actually flash is quite used, but in some cases, some flash also may be very radioactive. And red mud, nowadays I know there are a lot of publications regarding use red mud in the SS, but according our preliminary results, the red mud is quite radioactive. It cannot be used solely. It may, combine with other binders, but in practice, it is very difficult to judge whether this type of red mud is radioactive or not. So I think currently it is of great importance to judge this red mud in advance in practice. Another thing is allocation, the allocation of the environmental burdens. As we know, if we want to produce the PFA, the fly ash, it is the byproduct of the electricity. And in terms of GGBS or slag, it is the byproduct of the pig iron. But actually, it is not very fair to consider the PFA or GGBS as a pure industrial waste. Because if you produce a lot of electricity, it will give you a lot of environmental burdens. But some claim that you need to allocate the partial environmental impacts to the production of PFA or GGBS. So there are several allocation methods. That is allocation by mass, allocation by economical values. So after you adopt these allocation procedures, industrial waste may not be quite sustainable. But actually, people prefer the allocation, no allocation. Actually, but in our study, no allocation is also a kind of allocation process. So if you just adopt no allocation, so they are just consider them as industrial waste, I think they are quite sustainable. But if you allocate these environmental burdens by mass or economical values to the PFA or GGBS, so the industrial waste may not be that sustainable. So here comes the equation that is used to allocate the environmental burdens through mass or economical values. Another thing is, nowadays in some developed countries like UK, they already announced that a shutdown of all coal-fired power stations will be achieved in the near future. And GGBS, also another very commonly used material.
Ruan, you have 2 minutes left.
Okay, almost finished. I also face a similar situation in these developed countries due to the upgrade of the technology in the steel industries, so which also leads to a great decline in GGBS. So nowadays, China and India, they are the major countries that produces the flash and GGBS. So if you want to use these materials in other countries, the carbon dioxide emission associated with the transportation should also be taken into account. So finally is the conclusion. So I think first it is of paramount importance that the carbon dioxide recapture potential of the materials should be included in a life cycle, so which may alleviate the global warming potential induced by their production. Secondly, some alternative materials, including AAC or CSA cement, outperforms OPC from the perspective of carbon footprint and overall environmental impacts, while some are not really low carbon. Thirdly, the introduction of local solid waste in the alternative materials could further reduce the overall environmental burden to some degree, but some solid wastes should be re-examined. Okay, finish. Thanks.
Okay, thank you very much, Professor Ruan. And do we have any questions? Please raise your hands and we will unmute you. Do we have any questions? Okay, well, thank you very much, Professor Ruan. And we all know that the sustainable materials for the SS and it are very important and have very great potential in the application. So thank you very much. Uh, and if we have any questions, we can communicate with Professor Ruan privately. Okay.